Now we move on to study about mechanisms. Okay, here is the overall reaction. 5Br minus, BaRO3, 6H plus, blah, blah, blah. Slow step is Br minus plus H plus going to some intermediate. In other words, the slow step involves a bromide and an H plus. Nothing to do with the BrO3 minus, nothing to do with the other 4 Br minuses, nothing to do with the other 5 H pluses. The one step in the mechanism involves a Br minus and an H plus. So what happens if we increase the H plus? Well, if we increase the H plus, we're obviously increasing something involved in the slow step, in that rate determining step. Okay, and the more H pluses you have, the more collisions you will have that are important for the reaction or necessary for the reaction, and the more collisions you have, the more collisions that will overcome the activation energy you will have. So let's see what goes on here. Potential energy of the transition state decreases. Okay. Well, that's what happens when you use a catalyst in the reaction. Okay, the transition state, potential energy of the transition state is where you're at after the activation energy in a very simplistic sense. So therefore, a catalyst doesn't change the activation energy. A catalyst changes the activation energy. The H plus, the concentration of reactants, don't. Potential energy of the products decreases. Well, that's a thermodynamic issue. That's got nothing to do with how you get from the reactants to the products. The effectiveness of the collisions, no idea what that means. Okay, the number of collisions, absolutely. That's what we said. Okay, the more H plus ions you have, the more collisions, and you need those collisions from the H plus ions and the Br minus ions in order for that slow step to take place. The value of the rate constant changes? No, only changing temperature changes the rate constant. So a good question with all kinds of different concepts in it. Now we do a reaction coordinate. I love reaction coordinate diagrams because they show you what happens between the reactants, A, and the products, E, in terms of the energy. So you can see we start off, we have to go over one little hump to get to C. Well, C is not our stop at our finishing point, so we have to go a little bit further over D to get to E. Now, all kinds of things we can assign in this lovely little picture. As we said, A is a reactant, E is a product. Going from A to E, that change, delta E, sometimes delta H, depending what you're plotting, that is the heat of the reaction. You end up at E, you start at A. The heat of the reaction, the reaction change energy is E minus A. All of these are thermodynamic considerations. You start, you end, what's the overall energy between them? Kinetics is what happens in between. Well, there's two humps, which means there's two steps to get from A to E. C is what you make after the first step before the second step. That's called an intermediate. B and D are both transition states or activated complexes. There, you start at A, you go through B, that's the highest energy point, down to C, and then for the second step you go through D, that's the highest energy point, down to E. Now the second step is the higher step. That means that's the slow step. That's the one that's the harder to get over. Okay, so this would be a reaction where the second step is slower, and that's because the activation energy is the energy that you need to get over for the entire reaction. So it's not from A to B, even though B is the first step, it's the whole thing from A to D. So the activation energy, energy of D, minus that of A. I love reaction coordinate diagrams. Okay, reaction mechanisms. Overall rate law can be determined from the overall equation. No, we said that was totally wrong when we were talking about the rate laws. Species produced and consumed as catalysts. No, species that are produced and consumed are intermediates. Okay, intermediates are made, then used. Catalysts are there at the start, then get used up, but then get made again, so they're there at the end. The rate of the reaction, the rate of the fastest step? No, it's the rate of the slowest step. Chemical equation for the sum of all the elementary steps for the mechanism is the overall reaction. Absolutely. That's the very definition of a mechanism. Okay, again, if we talk about how I get from home to work, the mechanism is how do I get there. So I might go from home to the local petrol station to get a coffee, and then I might walk to another place and get a newspaper, and then I'll walk from there through the park to get to my office. Well, the overall thing, the overall process getting from home to work is the sum of all those things. If I don't have the bit from the coffee to the newspaper, well, then I'm not getting from home to work. Okay. Overall rate law determined from any step. No, it's only the slow step that gives you the rate law. So, reaction, oxygen and nitrogen make NO. Here's the proposed mechanism. What rate law predicted by the mechanism? Well, first of all, anytime you've just got a mechanism, you need to look at the reaction that it describes. So what I'm going to do is I'm going to add all these steps together. Okay, so I start with O2 and I make 2 O's. Okay, but then I don't see O2 anywhere else in the mechanism. I do see, however, I made 2 O's here, and I used one up and used one up there. So therefore the O's cancel out. The N's cancel out that I make in the second step, because I made an N in the second step and I used it in the third step. But now the O2, only starting, nothing else happened to it. N2, only at the start, nothing else happened to it. NO's not there at the start, but then I make them. So therefore the overall equation, O2 plus N2 goes to 2NO. Our reactants are O2 and N2. That is what appear in the rate law. Okay. Now, that rate law comes from the slow step. Okay, nothing else matters except the slow step in terms of determining the rate of the reaction. So let's find our slow step. It's step number 1. What's involved in step number 1? Only an O2, right? We used the nitrogen later on in the mechanism, but the slow step, only the O2 is involved. So therefore, the rate is going to be, rate is K times the concentration of O2. First order in O2, because there's 1 O2 involved in that slow step. 0 order in N2, because the N2 is not involved. The N2 only is involved later on. So the rate law K times the concentration of O2. Having a look at this question, H2O2 decomposes water and oxygen. Adding a small amount increases the rate of gas evolution. Okay, so FeCl3 isn't involved in the actual reaction, H2O2 going to water and oxygen, but what it does do is it increases how fast the reaction happens. That is the very definition of a catalyst. But now there's 3 possible answers with catalyst in there. Okay, heterogeneous catalyst is where the catalyst is a different phase from the reactants. Homogeneous is where it is in the same phase. Well, let's have a look here. In both cases, we got water, aqueous solution, water, and here the catalyst is in aqueous solution. So it's in the same phase. Thus, it is a homogeneous catalyst. Homeopathic catalyst doesn't exist. Homeopathic is all about a type of medicine, which we won't worry about here. So we got steps of a complex reaction. There we are. Only way to study a reaction when you've got the mechanism is you also need to know what the overall reaction is, so you can think about what the individual species are. So let's color code them and add together the whole thing. Let's start off. Ag+, it's obviously a reactant in the first step, so it gets used up. But then it appears again in the second step. So Ag+ is used up and then made. It cancels out from the whole mechanism, so it's not in the overall equation, but it's obviously very important, because if it wasn't there, you wouldn't get the first step. So something that's used, then made up, is a catalyst. So therefore, we could almost stop right there, but no, always go through and check everything else. So continuing on, we get Ce4+. Well, I see that made or used up in the first step, but not made again, so that's fine. Do get Ag2+. We make Ag2+. But then we use it up again. Something that is made, then used, is an intermediate. Continuing on, we get Ce3+. Well, that's made in the first step. Nothing happens to it later on, so that's just a product. Continuing on, we get Tl+. Well, that's a reactant in the second step, but nothing else, no other mention of Tl+, so that must make it an overall reactant. Ag2+, Ag+, we got rid of. Tl2+, we make in the second step, but we use up in the third step. So therefore it gets cancelled out, and again made then used, it's an intermediate. And then finally we've got another Ce4+ that we made. We got we got another Ce3+ that we made, and we got a Tl3+ that we made. So here's the overall equation, and to get from there to there, 3 steps, so a catalyst and 2 intermediates. Finally, just another emphasis of the definition of a catalyst. There's the energy, there's the overall profiles that we talk about in the movies. Example here, very high profile without a catalyst. Add a catalyst, lower activation energy, and a change in the mechanism. Okay, so an activation energy changes the pathway, changes the mechanism to lower the activation energy. So do we change the potential energy of the products? No, that's there, nothing to do with putting in a catalyst. Do we change the potential energy of the transition state? Yes, that's exactly what we do. Here's the potential energy of the transition state, the activation energy, that we lower it down there. So that's perfect. That's the very definition of what we do. Potential energy of the reactants decreases. No, that stays the same regardless. Energy of reactants, energy of products are thermodynamic quantities. Delta H doesn't change, again, thermodynamic products. And we've already said that there is nothing to do with the potential energy of the products. Catalyst, different mechanism, lower activation energy.